So let's finish this up from what you started on Friday. So hopefully this made sense. Hopefully you got a good review, a good understanding, a good basic understanding of basically everything we went through in the notes. So when you're studying, now you just can't use this explicitly. You actually have to go through your notes and pay attention to what's going on. Use this as a bonus added material, and it organizes it in a really good way so you can go through and look at some things. So on Friday, you did atomic radii, ionic radii, and valence electrons. Okay, today we're going to cover ionization energy, electron affinity, and electronegativity. So these are the three of the harder ones to know. These are the three that have a lot more content built into them. But it should not be as difficult, okay? So let's start with ionization energy. Well, the first thing I want to start talking about is what is ionization energy by definition, okay? But I want to explain it in terms that you can kind of relate to. When you add ation to a word, what does that mean? The process, okay? So what is ionization energy? The energy required to have a process to do what? Turn something into an ion. All right. So let's define that. We need to know what an ion is. What is an ion? Okay, very good. That's exactly right. It's charged. Okay, now let's talk about specifically how does it become charged? Okay, you gain or lose electrons. Okay, so you either gain or lose electrons. Now there are two types. What are the two types? Okay, very good. We have a cation. Okay, cation and an anion. Now, what is the charge of a cation? Positive, very good. And what does it do with electrons? Okay, it loses. Okay, what about the other one was the anion, and what's its sign? Okay. Everybody cool with this? Okay. Where? Anion. Because it just drives me at the wall. Okay, so now let's define the term ionization energy if you were to actually look it up in a textbook and exactly what it would say. So this is what it says. The energy required to turn an atom into an ion. Okay, we've already defined both of those. We've already defined a cation and defined an anion. Okay. So essentially what we're talking about is energy. Make sure you circle that. It all boils down to how much energy is required. And really what we want to do is we want to know how much energy is required to remove an electron. So if we're specifically talking about the ability to remove an electron, what are we trying to turn it into? Okay, so one more time. A cation. You're right. Okay, sorry, I was off topic in my head there. So yeah, when you remove an electron, when you lose one, we're specifically trying to turn it into a cation. Now, you need to know this formula right here, okay? It's not the most important one, but it's very important for your understanding in this. So, this atom, this element, whatever this is, just element A, is this neutral or charged? How can you tell it's neutral? Yeah, it's no positive or negative, okay? So what we want to do is we want to put some energy into this thing. Okay? When we put some energy into it, it's going to knock an electron off. So what you're going to produce is an electron and then an atom. If you knock an electron off, what's its charge now going to be? Positive. Very, very good. It's a plus sign. It's just like a chemical reaction. A plus B yields C plus D. Do what?
It looks like an actual arrow that's
No, but like the arrow is that the more I write his notes, the more the arrow.
Sorry. Now, the key here is we have to hit this neutral atom with some energy. What was that energy called we hit it with? A certain amount? Say it again. Who said it? A quantum. Very good. So this energy that we're specifically talking about is a quantum of energy. And what is a quantum of energy carried inside of? A photon. Exactly right. So see how we're tying all these topics back? This is exactly what we're trying to do. So this is what's going on in a ionization energy process. Again, the whole key word is how much energy is required to remove an electron. Now, what groups do you think the least amount of energy is required? Groups 1 or group 17? Okay, why group 1? It's got 1 electron. Is it easier to gain 7 or lose 1? Well, so it's easier to lose 1. Okay, so group 1 requires the least amount of energy. Okay. Yeah. Yes. It's all based on its charge and valence electrons. Because its charge will be +1 and it's got 1 valence electron. Yeah. All right, so let's talk about the trends, and this is the important part that you need to get. The trends are from left to right. It will increase. And again, when I say increase, what am I speaking about specifically? Okay, the energy, the amount of energy required will go up. We're getting there. So kind of hold that thought. Yeah. I'm talking about specifically how hard would it be to remove an electron? As you go left to right on the periodic table, it gets harder and harder and harder. So you have to have more and more energy. Okay. All right. So the reason why is, what is that all magical, wonderful, powerful word? Zeph. Okay. The reason why it gets harder is because you have more Zeph. And again, what does Zeph stand for? Very good. So how powerful is that nucleus with its ability to have all of its orbitals that are going around it to hold on to them and keep them pulled in as tight as it can possibly pull in? So that the further you go right, the higher the Zeph gets, the more powerful that nucleus gets. Now, essentially what else we can say is there's one more little thing we can add to this. The atom is smaller so it's harder to remove an electron. Okay. Again, the atom is much, much, much smaller, so it's harder to remove an electron. That is another way to get a look at it. And the reason it is smaller is because the Zeph is higher. Okay. So what do you think happens if you go down a column? It decreases. Very good. Okay, what specifically decreases? The energy. How easy it gets. Okay, how easy it gets. Now, if we go left to right, the atom itself gets smaller and smaller. What happens as you go down a column? It gets bigger and bigger. So let's kind of break this down into some words that we can think about. So the reason it decreases, can y'all see this color? Emily, can you see that in the back? Okay. You have more electrons. So since you have more electrons, you have more energy levels. Hold that thought, coming back to you. Can y'all see the brown in the back? All right, let's try this. That better? More energy levels. All right, so since you have more energy levels, somebody said it a second ago, what else do you have? More orbitals. Very good. Okay, so you have more more electrons, you have more energy levels, you have more orbitals. So in essence, what is happening to the size? Size is larger. Okay, size is larger. So if someone that's 400 pounds lost 5 pounds, would it be very hard to tell? No. Okay. 400 pounds loses 5 pounds. But what if somebody that was 75 pounds? Yeah, so the smaller it is, if you take something off, will you obviously notice? Yeah, but something that's so huge. Think about francium. It's got 87 electrons. It's got 7 rings out there. If you take one off that outer ring, would you even be able to tell it was gone? No. So that's kind of what I'm saying here. So the more electrons, the more energy levels, the more orbitals. So would it be really easy to take it from one of those 7 rings? Yes. Go ahead.
So when it's like left to right and down like column, will it ever be like the same? Or would it always be like one will increase and another one will decrease?
They're always going to be opposite. The only one that's oddly weird is the valence electrons. The valence electrons is the only one as you go down, it stays the same. That's the only one that's different. All the rest of them are increase or decrease, bigger or smaller. They're going to be opposite as you change. Okay? You'd have 7 rings. You'd have 87 total. Okay? All right. So let's do this real quick. So let's look at electron affinity now. What does affinity mean? To love or to like electrons. So electron affinity means your desire, your want, your needs, your love, your like for the electrons. So what group do you think has the highest affinity? Group 17. They love their electrons, right? Okay. So really what we want to know is they want to gain an electron. Okay, the more you love them, the more you want to get them. Okay, gain electrons. So again, we can add this in. Group 17 has the highest affinity. Okay, what group has the least? Okay, very good. So we can say group 1 is the lowest affinity. Okay, group 1 has the lowest affinity. And again, how do we know that? Group 1 has how many valence electrons? 1. Is it easier to gain 7 or lose 1? Well, they are screaming to get rid of that sucker. Let it go. I don't need it anymore. All right, so here is the definition. All right. Quotation marks. Okay. All right, so electron affinity is the energy. Conserve your space in this box, guys. Conserve your space in this box. Energy change when an electron is added. Okay? Last time, what did the equation look like? What was the final product of that ion? Was it a cation or anion, and the one above this? It was a cation. This time it says energy change when an electron is what? Added. So what is it turning into? Anion. Very, very, very good. So now we know that this is going to be an anion reaction. So do you notice the difference now? People asked me the other day, what is the difference between ionization energy and electron affinity? When it's ionization energy, it's talking about turning into a cation. When it's affinity, keyword, AA, affinity is an anion. Okay, easy way to remember that. Now, you will see these two formulas on the test. You're going to see one of the two, and you got to be able to pick out which one it is. Okay, so let's look at the first one. This was kind of what I talked about with, and you can put it under this, is stealing cookies. Okay. Now, when was it easier to take the cookies? When they were really, really close to me or really spread out? Really spread out, okay. So, that is a little bit of kind of what we're talking about here is the energy required when an electron is added. Now, there are some people that would literally walk by and try to grab all 3 of those bags. Okay. There are some of you, and I literally have to shove a bag in your pocket. Anybody like that? You don't want them? Okay. Okay. So let's talk about the people that would love to take them. You'd be so excited you would tell everybody that you saw. So we have this neutral atom. Okay. And what we're going to do is we're going to add an electron to it. Okay. And this happens without any trouble at all. It's like you literally walking by me, handing you a bag, and you jumping for joy. So what's going to happen is when you add an electron, what type of ion are you going to turn into? An anion. So it's going to become negative. And here's the thing that you're going to need to pay attention to, is where the energy value turns into. The energy is going to be a what? It is joule, but what side of the problem is it on? It's a product. The energy will be produced. What type of reaction has energy that is released? Say it again. Exothermic. Very good. This is an exothermic reaction.
So,
The electron will be a product.
what is just the A on the left side?
That's a neutral atom. And then you take an electron and you stick it to it, and it turns into an anion, and it releases energy. This is exo. This is like you walking out and being excited you have some cookies now. Okay? So, what group do you think takes electrons without any trouble? Group 17. Very good. So, anytime you have a group 17, it's going to happen naturally. You can walk up to them, and they're going to take that electron without any trouble whatsoever. Now, this is the other type of reaction. This is like me having to force you. So think of it in this terms. How many of you would have to literally force you to sit down and eat rutabagas? Okay, collard greens, you tell me. Okay, Brussels sprouts, spinach, any of those things, right? Okay, I literally have to sit down and force it in your mouth for you to eat it. So that's kind of like how some electrons work. So these are, you have the neutral atom, then you have plus electrons. So where do you think the energy would go now to have to force you to do it? It's an endothermic reaction, but where is the energy going to be? It's going to be a reactant. Very good. Okay. All right, so now we have the arrow, and it's going to be an anion. So what is the biggest key difference? The energies are on the opposite sides. So what is the reaction called when the energy goes into that reaction? Endothermic. Very good. So this one is going to be endo. Okay. And what groups do you think you would literally have to hold down and force them to take an electron? Group 1. Very good. Who said 4? No. That guy? All right. So when you're looking at this, I'm telling you right now, you will see one of these two on the test, and you're going to have to pick out which one is which. I'm going to say which reaction corresponds to the endothermic reaction, and you'd have to pick the bottom one. Or I could say which one corresponds to the exothermic reaction. You'd have to pick the top one. Or I could say which represents a reaction that would be most like a group 17 element, and you would pick the top one. So exactly. The key is, where is the energy? Okay. If it's exo, what does exo mean? To release, to produce, to make. What does endo mean? It's a reactant. You have to force it. Okay. All right. So let's talk about the trends and what happens within the trends. Okay. Go ahead and ask.
The energy on the right, why is it like, okay, I got it now. Okay.
You sure? Okay. So let's talk about the trends. So what happens as you go left to right? The electron affinity will do what? Increase. Very good. Okay. So why do you think it increases? Okay. There are more electrons, but what's happening to its outer shell as you go left to right? It's getting fuller, right? It needs more. So the reason that it increases is it has more of a need. Has more of a need for an electron. Okay, so really what we're saying here is more energy is released. Okay, more energy is released, and then you can even go one more step and even make it even more of a common thread statement, and that is to say that happy to get the electron.
Wait, Mr. Richard,
Yes, sir.
Why is it like the group 10? They have a full bill collection show, don't they? Because,
Group 10.
yeah, you have 2 on the lower one, 8 on the next one.
Okay.
I just totally.
Are you talking about the transition metals?
Yeah, he's talking about.
We completely ignore the transition metals. We completely ignore the D block. We never talk about the D block. You can read the chapter and learn about the D block, but it is completely weird and strange. But I don't teach it. I don't test it. I don't worry about it. Okay. All right. So the last part is, what do you think happens as you go down? It decreases. Now, what we know should happen in life, those people that are 400 pounds probably shouldn't be eating McDonald's double cheeseburgers. So we can't really use that example here. But what is happening to the size of an atom as you go down? It's getting bigger. So what is happening for its love of electrons? If you've got 87 electrons, do you really need another one? No, you are trying to find any way to get rid of it. So the size increases. So what does that tell me about the desire to gain an electron? There's less desire. So really what you could say is there's less energy involved. So again, just like I did with the cookies, the bigger the size, the further those cookies have got away from me. How hard would it have been for you to take that bag as you walked out the door the further it got? The easier. Well, the bigger these things get, the less energy required. Because I couldn't have caught up with you. Yes, sir.
But the last one, like the bottom one on group 17.
Let's just say iodine, 53.
Yeah, so it has a less affinity than the fluorine.
Exactly. A lot less of affinity. Because it's so large, it's like, I've already got 53. It is still higher than anything to the left of it.
It's basically like
Hang on. Because it's in group 17, it only needs 1. It still has more affinity than, say, something in group 16 because it needs 2. Even though it has 53, it's lugging all these 53 electrons around. It's like, okay, I really just want 1 more. I can stick 1 more. But someone like 87, they're like, I've got 1 extra that I don't need. I want to get rid of it. Okay, Tyler? Yes. And does the energy change when you gain it? Sir? Fluorine, it has the highest affinity, yes. Okay? It has the highest affinity. All right, any questions on this?
How do you get a
How do you get a what? How do you get a cation? You have to lose an electron. Someone has to take an electron from you. Okay. Last topic, electronegativity. Now, this is the one that I think I love talking about the most, is because it makes sense to me. And this is the bullies versus the nerds. Okay. So what group are the biggest bullies? Group 17. Very good. Okay. What about the biggest nerds? Group 1. Very good. Okay, group 1. So, who is the most electronegative? Fluorine. Very good. So, since fluorine's the most electronegative, what does that tell you about him? The biggest bully.
He is a joke.
Okay. Now, and I've told you this before, the way I abbreviate electronegativity is eneg. Okay, I'm way too lazy to write that whole word out. So, fluorine is the most electronegative. So, therefore, he is the biggest bully. Okay. There's one little, I tell you what, let me move on before I do this. I want to give you the definition in the book of, if you were to read in the book, this is what it says. The electronegativity is the ability. Have I passed out test objectives?
How long is it?
It's 55 questions as of right now. It may be 60, that's it. But it's all multiple choice. Okay, count out how many you need and pass them back. Okay. Underneath the Mac. No, on the right. Thank you. Thank you. Okay, so there's the definition of electronegativity. Please finish writing this down. The ability of an atom to attract an electron from another atom while it's bonded to it. And the key word here is bonded. So what I need you to think about is think chemical bonding. Okay? Think chemical bonding. And there's a very important topic here that we're getting into the very next chapter, but I'm just going to go ahead and teach it to you so you know it. You don't have to think about it. Okay? Electronegativity. Electronegativity is the cause for polarity. Okay? Electronegativity causes polarity. And I know what you're thinking. What are you talking about as far as polarity? And again, it's a very common idea. It's a very simple aspect. And what I mean is, what if I were to take H and F and I were to chemically bond them together? What does that line between them represent? It represents a chemical bond. Now, do you agree that they will be sharing that electron? Yes, okay. Who is the bigger bully? Who is more electronegative? Okay, this was that. Remember I said if you have an older sibling, if you're trying to share a toy, who gets to keep it more often? The older sibling. So if I take this electron, okay, and I spin around once, who is going to take it the second time? Fluorine. And then all of a sudden it's just going to say, okay, well, I'm just going to keep it and keep it and keep it until you get this obviously disproportionate, unbalanced sense that fluorine is obviously keeping that electron a lot more often, right? Okay. Now, what we have is we have this thing they create poles. Okay. And I wrote this little thing. What does that little symbol stand for? I said slightly, but it represents a different word. It was partial, okay? So is fluorine slightly negative or slightly positive? What does it have going around it more often? It's got an electron. So if I stick an electron around you, what are you going to turn? So you're going to turn slightly negative. Now, why is it slightly and not fully? Because it's still sharing. That's exactly right. So it doesn't own it 100%. So it's still kind of sharing it back and forth. Well, if fluorine is slightly negative, what does that make? What does that make hydrogen? Positive. Very good. Now, there's two types of these names. There's polar and there's non-polar. Have poles been created? So what is this? This is polar. Very good. So anytime you have an unequal sharing like this, you have something that is polar. Okay. Well, let's look at the opposite of that. What if I take H and I bond it with another H? Are either of these stronger than each other? No. So what do you think you're going to get here? It'll be equal sharing. Okay, so it's just going to go back and forth just like this. And it'll be obvious that neither one of them is stronger than the other. So no poles are created. So what would this be? Non-polar. You're starting to get the picture. Okay. So that is non-polar. And again, that is all the next chapter we're fixing to get into. So when I start teaching this, you're like, this is boring. I get this. Move on. Good. I want you to be able to say that. Okay. All right, let's talk about the trends. Well, these are the easiest two trends because we've covered them so often that you should get it by now. These electronegativity values increase as you go left to right. What is that big magical word for the reason why? More Zeph. Why do you not like that word? Oh, I got something to tell you real quick. Anybody ever?
If you go to eat with your family and they ask for ketchup.
Okay, so let's finish this up. So increase, you have more Zeph, and then as you go down, it will decrease. And again, what has been this common theme of the reason it will decrease? Okay, very good. There are more orbitals. Okay, so the size will increase. The biggest reason why. Don't put this up. I got one more thing I want to add. And I need to go back up and talk about it because I forgot to talk about it at the beginning, but I wanted to finish it before I talked about it. Size increases. Sorry about that. Pen messed up. So again, it gets bigger, gets a little bit harder to go be a bully. Okay? So again, hopefully this will kind of give you a good study tool to use as you're working through the notes and kind of like, okay, and being able to mentally map it out in your head. What I need you to do is I need you to go back up to ionization energy. Let me pause this real quick. Hopefully. Now, ionization energy. Here's what I want to talk about. This is how I want you to think about it, and I want you to write it however you need to write it for you to understand it. If you took one bag of cookies from me, congratulations. Now, do you think it would become easier or harder to take a second bag? It will become harder. So translate that in terms of energy. Would it require more energy or less energy? More, okay? What if you then tried to take a third bag? Be harder or easier? Even harder and what? More energy. Okay, so this is how I want you to read it. The more electrons you take, the blank the energy required. The more energy required. So however you need to rephrase that, that is going to be on your test, is the reason I'm telling you this. Okay, ionization energy. The more electrons removed, the more energy required. And I'm going to show you what I mean. The more electrons removed, I would write that down. The more electrons removed, the more energy required. And so this is an example. And guys, if you ever see this in the book, I want you to understand what it means. Do what? So what do you think IE1, IE2, and IE3 stand for? Okay. The energy required to remove how many? 1. Ionization energy to remove how many? 2. And then ionization energy to remove 3. All right, so let's talk about this. What if you looked it up in the book? The first energy required was, let's just hypothetically say it was 100 joules. The second one was 200 joules. And then the third one automatically, for some weird, strange reason, jumped up to 7,000 joules. Is there a huge, obvious difference here? Yes. What do you think would be the cause for such a huge, drastic jump, and how hard it would be to remove an electron? Okay. Let's think about this. What if I had magnesium? Okay. Magnesium has 12 electrons. So the first one would be 2. The next one, crap. All right. The next one would be how many? 8. And then since it's in group 2, it's going to have how many valence? It's going to have 1 here and then 1 here. So now group 2, do they want to gain 2? Do they want to gain 6 or lose 2? They want to lose these 2. So do you agree that they're willing to lose those 2 electrons fairly freely? Yes. Now, the first one we got rid of, 100 joules, right? No big deal. Now, does it get a little bit harder to remove a second one? Yes. So what happens when they lose the second one? Then all of a sudden, 7,000? Why? Because what you've just done is you've entered the second orbital. And what is very significant about this second orbital? It's got its octet. It's complete. So is it going to let go of any of these 8? No. It is almost impossible. So right here, what you have done is you have dropped orbitals. You have fallen into a complete orbital. No, it is almost impossible. And that's the reason why this value is so high. When it goes from 200 to 7,000, there's nothing out there that can come and take one of its 8 electrons. That's why, and if you ever notice in a table, it will drop that far because of that reason. What you have done is you have established this reasoning for too much energy to overcome to remove any of those electrons. Okay? Yes, sir. Okay, good example. Let's talk about that. What if it was boron? Okay, boron has 5, so it's got 2, and then it's got 3, 4, 5. Okay, well, IE1, IE2, IE3, and then we'd have to go all the way to IE4. Where would be the hugest jump between now? Between 3 and 4, right? So it would be some number, and then let's just 1,000,000. Okay, and now, again, I'm making this up, but it would be a drastic jump between 3 and 4. And the reason you can tell is because, well, that's the first one, that's the second one, that's the third one. You just jumped an orbital down. Okay? A huge change. if it has 3 valence electrons. What if it has 1 valence electron? It will be between 1 and 2. It will be 100, and then it would jump up to 5,000. So it'd be such a big change, you would say that's where the orbital change is. Okay? Does that make sense in ionization energy? So again, it gets harder, and then all of a sudden there's a huge, drastic jump because it gets into an orbital that's stable and it's got a full octet. Okay? Any questions on that? All right, very good. So hopefully that will help you guys study for the exam. Okay.